Semiconductors are often described as the oil of the digital age, but there is another resource that matters just as much, yet receives far less attention: water. Now, China's new $50 billion water chip factory project focuses primarily on this invisible resource. But before we get into it, make sure to subscribe to our channel for more deep dives into the hidden infrastructure behind global power, the hidden ingredient behind every chip. When people think about chip manufacturing, they mostly imagine lasers and machines that cost more than skyscrapers being used in clean rooms. But what they never imagine is water flowing endlessly through pipes hidden behind the walls of the labs. The fabrication of modern semiconductors depends heavily on ultrapure water, which is often abbreviated as UPW, and it is used in staggering quantities. Every silicon wafer has to be rinsed, cleaned, soaked, sprayed, and polished dozens of times before it finally becomes a usable chip. Ultrapure water is not just filtered water that is used for this purpose, but it is actually water that is stripped almost of everything that makes water naturally exist in this world. It has no minerals, no salts, no bacteria, no organic molecules, and almost no dissolved gases. Even a single stray ion or a nanometer scale particle can ruin an entire wafer full of chips at the most advanced nodes. That is why fabs consume millions of gallons of water per day, and that is way purer than anything humans drink, bottle, or even inject. This requirement makes water a strategic resource, and countries that can secure, purify, recycle, and control enormous volumes of ultrapure water are the ones who gain a decisive advantage in advanced chipmaking. China recognized this reality, and it is going to build factories that prioritize water first and chips second. What ultrapure water really means. Ultrapure water is one of those terms that sound simple on the surface but get complicated when you start examining it. But you can understand it, as clean water in ordinary life refers to water that is safe to drink. But in semiconductor manufacturing, clean water means water that is almost chemically empty. The electrical resistivity of this water is pushed to its theoretical maximum, and it indicates that all the ions are removed from it. Absolutely pure water has a resistivity of about 18.1 megohm centimeters at room temperature. And that number is considered a holy grail inside chip fabs because even a tiny amount of sodium, potassium, chloride, or boron ion can lower it. The tolerances are so extreme that contamination levels have to be measured in parts per trillion. To put this into perspective, you can understand it like you will have hundreds of times more chances of winning a national jackpot than finding a random sodium ion in semiconductor-grade ultrapure water. Particles are even more dangerous than this because a particle is smaller than a virus, and it can easily lodge itself between circuit features, which can cause a short circuit, a broken transistor, or a defect that can silently kill performance. As chip features are continuously shrinking into single-digit nanometers, the allowable particle size is also shrinking along with it. This type of relentless tightening of basic standards is one of the main reasons water systems are becoming so expensive and complicated in today's age. Why water purity directly controls yield. Yield is the one unglamorous metric that decides whether a chip factory would be able to make money or is going to burn it, and yield is measured by how many usable chips can be taken out from a single wafer. So when yields are low, even the most advanced process node becomes economically useless. Impurities that are present in water have several ways to attack yield, as particles can block or distort lithography patterns, much like the way dust on a camera lens creates a blur or shadow in the image. On the other hand, metallic ions can diffuse into silicon to alter the electrical properties. Organic contaminants can decompose under ultraviolet light during the lithography process, which creates reactive byproducts that could damage the delicate structures of the chips. Even the gases present there can form microscopic bubbles that could interfere with surface chemistry. It has been seen in history that entire generations of chip processors had to struggle a lot because of these kinds of water-related defects. Engineers spent several years pushing yield from barely viable levels to commercially sustainable ones, and as nodes advance, the margin for error shrinks. But this also makes water purity one of the hardest variables to control. The categories of contamination engineers fear. The engineers who work inside a fab have to think in categories of enemies, and their first enemy is particles, because anything solid can shed fragments. All pipes, valves, filters, and even the resins used in purification systems slowly erode due to constant flow. What makes these particles especially dangerous is the fact that they do not appear steadily, but they actually come in bursts. The second enemy is biological life, because bacteria love water systems, especially when water stagnates, and even dead bacteria are quite bad as they leave behind organic residue to feed the future growth. Modern cleanroom practices are designed to reduce this risk, but still, new facilities often struggle with bacterial control during ramp-up. The third enemy is definitely organic carbon, because total organic carbon serves as food for all the microbes, and it can leave residues on wafers, so even the trace amounts of carbon matter heavily in this process. The fourth enemy is silica itself, which is abundant in nature and can appear either dissolved or as particles. This is considered an enemy because discrete silica particles are particularly destructive to semiconductor yields. And then finally, there is everything else to disrupt the yields, including metals, ions, and dissolved gases. Each of these can quietly sabotage device performance, and removing all of them at an industrial scale is impossible. But removing everything measurable is the standard that this industry has adopted. Standards that border on absurd. Even 2 decades ago, when leading-edge features were measured in hundreds of nanometers, water purity standards were already extreme. Because the maximum allowed particle size in ultrapure water at that time was roughly half of the feature width. This meant that tens of nanometers and only a handful of particles per liter were allowed. But as process nodes advanced more and more, these limits tightened relentlessly. Ion concentrations were dropped into the single-digit parts per trillion range, and particle limits fell below the detection capabilities of existing instruments. Engineers found themselves in quite a strange position because they had to control contamination that they could not even reliably measure because of a lack of advanced instruments. This is the time when water systems stopped being ordinary chemical engineering projects and started becoming exercises in probabilistic risk management. The entire goal of these projects was shifted from perfect measurement to preventing worst-case scenarios through design, materials selection, and aggressive maintenance, all at the same time. If you are enjoying this video so far, then do subscribe to our channel for more deep dives into engineering and infrastructure marvels, from raw water to the purest substance on Earth. Turning ordinary water into something clean enough for use in the manufacturing of advanced semiconductors is not a single process, but it is actually a layered transformation that resembles alchemy. Every ultra-pure water system begins with raw input, but that input can vary wildly depending on geography and climate. Municipal supplies, groundwater, surface reservoirs, reclaimed wastewater, and even seawater can all serve as static points, while each of them brings its own contaminants and risks. The thing that matters is not the source itself, but the fact of how predictably it can be stripped of everything except H2O day after day without any further interruption. The purification journey consists of multiple stages, and each is designed to eliminate entire classes of contaminants. Pre-treatment removes suspended solids, chlorine, and quaparticles that would otherwise damage the downstream of this system. Reverse osmosis flows while forcing water through semi-permeable membranes under extreme pressure to reject most dissolved salts, organics, bacteria, and viruses. The thing that emerges after these 2 stages is dramatically cleaner, but it is still far from pure enough for being used in the manufacturing of chips that could be measured in nanometers. After reverse osmosis, the water is degassed to remove dissolved oxygen and carbon dioxide. Then, it is further exposed to ultraviolet light that breaks apart all the remaining organic molecules into simpler forms that could be easily removed later. Ion exchange systems then strip away the lost charged particles to push electrical resistivity toward its theoretical maximum. Finally, the water is entered into a continuously circulating polished loop where it is kept in constant motion through ultrafine filters. This flow never stops because stagnant water invites bacteria, biofilms, and chemical instability. So, this entire system has to run non-stop with redundancy that is built into every critical component because even minutes of failure can cost millions in lost production. The thing that actually makes this system so extraordinary is not just its complexity, but also its sensitivity. Because the tighter the chip geometry becomes, the more unforgiving the water system grows. So every new process node pushes water purity requirements closer to the limits of physics, while it simultaneously increases the volume of water that is required for the manufacturing process, measuring what cannot be seen and controlling what cannot be measured. One of the great paradoxes of ultrapure water engineering is that the most dangerous contaminants are often too small to detect reliably with the help of existing instruments, and engineers cannot simply measure everything and react accordingly. Instead, they have to rely on indirect signals and statistical inference. Sensors are scattered throughout the piping network to provide real-time feedback, allowing engineers to detect deviations before they reach critical points. Particles are far more difficult, because laser-based scattering instruments can detect particles down to a certain size, but as chip features shrink into the single-digit nanometer range, the so-called killer particle becomes smaller than what existing tools can consistently identify. This gap between what must be controlled and what can be measured is known as the metrology gap, and it has become a defining constraint on advanced manufacturing. Fabs rely heavily on proactive risk control because the gap cannot be closed technologically. Larger particles are measured upstream, where detection is still reliable, and mathematical models are used to extrapolate the likely population of smaller, invisible particles downstream. This approach is paired with obsessive material selection, aggressive filter replacement, and constant system flushing. It is not certainty that keeps yields high, but it is actually the discipline that does. As process nodes advance, this fragility only increases. Every additional fabrication step adds another opportunity for contamination, another rinse, another polishing cycle. Why the United States faces structural limits? The United States has the technical expertise to build world-class ultrapure water systems. But expertise is not the bottleneck here. It actually is the geography, governance, and time. Many new fabs are being constructed in regions where water is already scarce and politically contested, while any proposal to divert, reclaim, or desalinate water can trigger environmental reviews, legal challenges, and negotiations across multiple jurisdictions. Unlike China's centralized planning model, the US system distributes authority across federal, state, local, and private actors. So, each layer introduces delays and uncertainty. Even when funding exists, projects can stall for years. Money cannot compress permitting timelines, override local opposition, or guarantee long-term water rights. A $50 billion budget does not change the fact that large-scale water infrastructure in the United States must earn social license before it breaks ground. This reality makes China's approach extraordinarily difficult to replicate, regardless of intent or resources. China's $50 billion water chip factory is actually about mastering the invisible infrastructure that makes advanced technology possible, rather than being just about semiconductors. Ultra-pure water has become a strategic resource, and China has already started treating it as such. The United States can compete, but only by confronting structural limits that money alone cannot solve. Now, if you enjoyed watching this video, then do subscribe to our channel for more breakdowns of innovative technology.